Two frozen worlds are burning from the inside. Science just caught up. For 50 years, Uranus and Neptune were textbook ice giants. Rocky cores wrapped in layers of water and methane ice, crowned with hydrogen and helium. That model was settled. Then, in mid-June 2026, a paper rewrote everything. Edward Young and his team modeled the interior of these two worlds not as ice giants but as magma ocean planets. Beneath the hydrogen-helium atmosphere lies a vast magma ocean, silicate and iron, melted under crushing pressure, churning in a roiling sea of heat and chemistry. Every measurement astronomers had taken aligned with this new model. Radius, density, magnetic fields, the heat they radiate into space. Properties that had never quite fit the old model suddenly made sense. But if we were so wrong about two of the most studied worlds in our solar system, wrong for 50 years, what else might we be misunderstanding? The answer matters more than you might think. A magma ocean is not metaphor. It's a real sea of melted rock and metal, kilometers deep, churning inside a planet. Imagine the oldest oceans on Earth, before water filled them, oceans of liquid stone. Under extreme pressure and heat, silicates and iron melt into a fluid state. The model places this ocean beneath the hydrogen-helium layer, separated by a transition zone of mixed composition, oxygen, magnesium, silicon, and hydrogen mingling at the boundary between the molten interior and the gas above. Why does this work, where the ice model failed? Start with magnetism. Uranus and Neptune both generate strong magnetic fields. Ice is not electrically conductive. The magma ocean is. Molten iron and silicate, churning under pressure, create the dynamo effect, the same mechanism that generates Earth's magnetic field. It explains the field strength. It explains the field's asymmetry, the way the field is tilted at odd angles to the planet's spin. A puzzle that had baffled researchers for decades found its answer. Density is another mystery solved. The old model predicted where the mass should concentrate inside the planet, based on icy mantles and rocky cores. Measurements of gravitational gradients, how gravity changes with latitude, contradicted it. The magma ocean model fits. Intrinsic luminosity match too. These planets radiate more heat than they receive from the sun. Where does it come from? A magma ocean, slowly cooling and releasing energy across billions of years, accounts for it. The pieces aligned. This discovery does more than rewrite textbooks about our solar system. It rewrites how we understand planets across the galaxy. Uranus and Neptune are not unique ice giants. They are analogs, examples, for the most common exoplanet type, sub-Neptunes. These are worlds with radii between 1 and 4.5 times Earth's radius. Thousands have been discovered in the past 2 decades. Astronomers have puzzled over their nature. Are they mini ice giants losing their atmospheres? Mini gas giants? Hybrids? The problem was straightforward. We had no local examples to compare them to, until now. If Uranus and Neptune are magma ocean worlds, not ice giants, then many sub-Neptunes might be too. Many orbit much closer to their stars. Heat is extreme. A magma ocean world with a conductive interior, a thin solid crust, and hydrogen-helium envelope could survive that heat more easily than an ice giant could. The model suggests sub-Neptunes might not be de-thawing ice giants in the process of losing their atmospheres. They might be born as magma ocean worlds. They might have always been this way. This reframes exoplanet science. For the first time, we have a testable hypothesis for the interior structure of the most common planets in the universe, not from theory alone, but from 2 examples in our own neighborhood. Future observations of exoplanet atmospheres, their magnetic fields, their rotation, all of it might confirm whether sub-Neptunes truly share this magma ocean nature. For now, the discovery offers a new lens. These worlds might be far more alien, far more dynamic, and far more like active molten planets than anyone imagined. Yet the magma ocean model raises as many questions as it answers. How did Uranus and Neptune acquire such massive hydrogen-helium atmospheres? Standard formation theory says planets grow by accretion. Dust collects, rocks form, they collide and build up. When they grow large enough, they pull in gas from the surrounding nebula. But when did this happen? In what order? If the magma ocean cooled and solidified before the atmosphere formed, the interior would be different. If the atmosphere formed first and the interior melted later, the sequence matters. The researchers showed their model was thermodynamically possible, but it doesn't fully resolve the formation history. There's also the question of what's happening inside those magma oceans right now. Are they actively churning or slowly crystallizing? If they're cooling, they lose energy into space. The luminosity measurements suggest ongoing cooling, but over what timescale? Millions of years? Billions? Understanding the dynamics, the convection, the chemistry, the phase transitions at different pressures and temperatures requires models we're only beginning to build. The boundary between the magma ocean and the hydrogen-helium atmosphere is not a simple wall. It's a transition zone where silicates, iron, oxygen, and hydrogen meet and mingle. The chemistry there might be exotic and active. Reactions might occur that shape atmospheric composition. We detect methane and ammonia in both atmospheres. Where do they come from? Are they primordial remnants from formation, or are they produced by chemistry at the magma-ocean boundary, then carried upward by convection and diffusion? We don't know. The discovery that Uranus and Neptune are magma-ocean worlds doesn't close the door on our understanding. It opens one. Every measurement of their atmospheres, every signal from their magnetic fields, every observation of their rotation and internal structure, all of it now carries new weight. These are not dead, frozen worlds. They're active, dynamic, molten at their cores, still radiating heat into the void. And if they are this way, thousands of exoplanets across the galaxy might be too. The question now is not what we were wrong about. It's what else we might be wrong about. In a universe that keeps rewriting itself when we look more closely, that's exactly the kind of question that drives science forward.